Okay, so this is the heat of reaction lab. Let's go over the lab itself, and then I will write out a couple tips that should help you when you are completing the lab. So let's look at the background. They're talking about exothermic and endothermic reactions. And this, what they're showing here in figure 1, is an endothermic reaction. Okay, so it absorbs heat. So that's where, when we were doing the chemical change lab, remember when we would test, the test tube would feel extra cold when it was, the heat was being absorbed into the reaction. So sodium carbonate, when it reacts with hydrochloric acid in a solution, is an endothermic reaction. It will absorb the heat, so the you would feel like a cold test tube on that one. An exothermic reaction releases heat. So let's look at this. When magnesium metal reacts with hydrochloric acid, the reaction's exothermic, so it releases heat. What we're doing in this lab is we are going to be measuring the heat that's released or absorbed by a reaction. This is called the heat of reaction. And you're going to be looking at this symbol here where it says Q reaction. That is what is representing the heat of the reaction. So the reaction can be performed in a container called a calorimeter. So had you guys been in the lab, I'm going to scroll over here. This is the setup that you would have been doing. So there's a glass beaker that has a couple insulated styrofoam cups in it. There's a glass stir rod, and it's set up with a ring stand, and there's a top that goes onto it. Now this is kind of like a foam, like a thick foam, almost like a heavy styrofoam, and it's got a cutout in it that matches the shape of the top of the beaker. There's a black thermometer holder, and that's for us to put the thermometer in. But what it is that is allowing it to go down into the calorimeter bottom. So when we hook them together, we would be lowering this top part down onto the calorimeter to create a closed system. So what we're talking about here is, you guys know the terms conservation of energy, where it can't be created or destroyed. And we're going to be using this calorimetry, where total energy in a system is conserved. We're going to be creating a closed system where we'll be able to take some temperature measurements and monitor the changes. So let's go back up here. That's what's drawn out here. Here's the calorimeter where all the heat's absorbed by the water that's in the solution. So you're going to see some equations here. And what these equations are, the Q, water, is the heat that's absorbed by the water. The M, water, is the mass, so that is in grams, okay? SH is specific heat of the water, times this triangle T is the change in temperature. So change in temperature is the T final minus the T initial. We're going to be taking a couple different temperatures of the heat, measuring what's inside the closed system. So the final temperature that we get, we're going to subtract our initial temperature, and that's where we get our triangle T. The triangle stands for change. We are going to be looking at the Q water equaling a negative Q of the reaction. It is going to be negative, if we read through here, the heat absorbed is equal to the magnitude of the opposite in sign. So it depends on the heat, and so it's usually reported as negative. So that's why it says negative Q, okay? And then we're going to be calculating, use the change in H of the reaction is going to be equal to Q times the kilocalories over N, which is the number of moles. And I know that's a lot of equations to look at once, but we'll kind of break it down a little, okay? So what we're using in this experiment, hydrochloric acid and magnesium metal and magnesium oxide, which is a white powder. We took some pictures, you'll see when you go down here. Okay, so these are little pieces of magnesium metal that are going to be added into the bottom of the calorimeter. So that's the styrofoam cup from the bottom that is containing the hydrochloric acid. And you can see here that there's bubbles that are forming because it is quite reactive. Okay, and then the magnesium oxide is this white powder that is also being put into a cup at a separate, we're doing two separate reactions here. So we are adding this into a cup that has the hydrochloric acid also to check and see. Can't see it here, there's not much going on, okay? All right, so let's look at our procedure. So we added 100.0 milliliters of 1 molar hydrochloric acid into the calorimeter bottom. It was assembled and we put the top down, so it was making the closed system. We had the thermometer in there. And we measured out 0.50 grams of magnesium. And then we added that into the calorimeter, covered the lid again, and gently mixed with that glass stirrod. So we were pushing it up and down to make it mix. And the temperature was recorded, okay? If you look down here, we'll come back to the second reaction in a minute, we gave you the results. So you're gonna be using the results that are here on this page to do your calculations. So this reaction 1 is with the magnesium metal and the hydrochloric acid. We have the mass in grams. We have our initial temperature, we have our final temperature, and then we give you the change in temperature. So we have T final minus T initial. Okay? You're gonna now perform, or we performed, you're gonna use the, the virtual lab. We did the same thing, except this time we weighed out 1.00 grams of magnesium oxide. Repeated the same procedure, and we recorded the results. So here's our mass in grams of the magnesium oxide, our initial temperature, our final temperature, not quite as big of a jump as when we had the magnesium metal. And this is our change in T, our final minus the initial. Okay. So let's look at what they're asking you to do on the calculations, and then I'll kind of just give you some little tips that I would have put on the board had we been in class. So using dimensional analysis, we're going to calculate the number of moles of magnesium used in the reaction. So this is where you're going to be taking the grams and converting it using molar mass from the periodic table. Then we're going to calculate the heat absorbed by the solution using this equation. And what you're doing basically is you're just plugging things in. This is what I'm going to write out on a piece of paper to kind of give you a little more detail, just a couple more hints, okay? You're going to go through and you're going to calculate the change in H for the reaction, and you're going to be converting it to kilocalories, okay? You are going to be then calculating percent error. So remember, theoretical is how much should be able to be produced. Experimental is what we did in the experiment. Okay, so you're going to plug those in and multiply it by 100 to get a percent. And then we're going to be using this, we're going to convert the experimental into kilojoules. Okay, so we gave you this here, 1 kilocalorie equals 4.184 kilojoules. And then you're going to repeat the process with the other experiments. So now you're doing the same thing, dimensional analysis, calculating the number of moles of magnesium oxide. That's where you're going to take the grams used, multiply it by the molar mass from the periodic table. Okay, and convert it to moles. Same steps as the other experiment that we did. So we're just doing it with both experiments. Okay, so I'm going to pause this for a minute, and then we're going to go over to the whiteboard, and I will show you just a couple tips, okay? Okay, I am having problems with my webcam. We had a power outage last night, and so there's a lag while I'm trying to write and talk at the same time. So I wrote out all of the information. My arm is not right in front of this right now, by the way. It'll move in a minute. There we go. Okay, so I wrote out some of this. So I'm going to talk you through this, and I can scan and send this to you, okay? So this is what I would have put on the board if we had been in lab. We've got heat gained by the solution is equal heat lost by the reaction. So that's what we're going to be measuring and calculating, okay? So the heat gained by the solution, we have Q equals M times SH times change in temperature. So the M is the mass of the solution in grams. The SH is the heat capacity of water. And the change in temperature is our T final minus T initial, like I had shown you in the other one. Now I'm trying to move the paper up. It's going to be just a delay for a second here. This is interesting. We had something blue on one of our main transformers, but they've got it back up and going. So here, just a little bit of a lag on my small table here. Let me see if I can get this all the way up. Apologies. There's going to be 4 steps that I'm trying to get onto the video capture here. Oh, keep moving. Okay, so let's look at step 1. We've got Q is going to need to be in calories, right? We are going to be converting calories to kilocalories. That's step 2. Step 3, the change in H is kilocalories divided by the moles of the magnesium for reaction 1, and then the moles of magnesium oxide for the second reaction, the second experiment. Okay, so what I wrote on number 4 is, since this is the heat lost by the reaction, the change in heat, the change in H of the reaction, that RXN stands for reaction, should be negative. Okay, so hopefully this is enough of a start for you for the lab. Go ahead and email me if you have questions. Hopefully I can get my webcam up working, and if we need to, I can do some more videos. But this should get you to where you need to be. Okay, so good luck, and just email me if you have any questions on this or anything else. Okay, hope you guys are all doing well.